So we've been working from the bottom up, and what we've done so far is to look at some specific examples of 3 points, but we said that the first thing we need to do is determine all the 3 points. So far we just did the massless case. And what I want to do today is to continue to 4 points, discuss how we determine the 4 points, still at the massless case. And in particular, we said that if we work bottom up like this and demand that the amplitudes are consistent, we can recover many things that we know from Lagrangians. So the first thing we'll see today, by looking at the 4 gluon amplitude, is indeed the Jacobi identity. And then the other thing that I want to do in this story, this first example is going to be completely brute force. And then I want to describe for you how recursion relations work at a very superficial level, just so you see how things work. And if you want the details, then you can complete that later. And then once we do that, I want to switch to the massive case and again talk about the bottom-up construction of amplitudes. And then the next thing that we're going to do is we'll talk about EFT applications. So hopefully we're going to finish this part today pretty much, and then we can talk about EFT applications tomorrow. And again, just like we already saw some examples of how we recover things that we know from QFT using this bottom-up construction. So in the bottom-up construction of massive amplitudes, we'll also see some elements of the Higgs mechanism emerge. So this is the plan for today and then tomorrow. Okay, so we finished yesterday by talking about the analytic structure of 4-point amplitudes. And this is what we're going to use today. So the example that I want to start from is the 4-point gluon amplitude. And at this point, we don't know that these are gluons, right? So for us, these are massless spin 1 particles. And let's imagine that there are n of these guys. So there are n such particles. Okay, so I want to look at the amplitude where I have 2 positive helicity gluons going to 2 positive helicity gluons, but let's take them all to be incoming. So I'm looking at the amplitude with 1a minus, 2b minus, 3c plus, and 4d plus. And these a, b, c, d indices run over 1 to n. And the minuses and pluses are the helicities. Okay, so we talked about the little group and what it implies about the amplitude. And in this case, we have 4 vectors. So each one of them should appear twice with either angles or squares. So the little group scaling tells us that the amplitude has the following form. It has to have 1, 2 square, 3, 4 square, and then there is some function f, a, b, c, d of S12 and S13, for example. So this is specified by the little group. And then the only thing that can multiply that is something that's invariant under the little group. So it's neutral. And the Mandelstam invariants are neutral under the little group. So here I can have some function, and it's carrying these A, B, C, D indices. Okay, now, and I used here the fact that S12 plus S13 plus S23 equals 0, so there are only two independent Mandelstams that I can work with. Okay, now this is a 4-point amplitude, so its dimension is 0. And here we have 4 powers of these guys, so that means that the dimension of this f here is -4. So this is something that we're gonna use. And the first thing that the thing that I really want to use now is the analytic structure of this thing. So we said that this f is an analytic function of the S's, and we know that it only has simple poles. It can only have single particle poles when one of these Sij goes to 0. So the other thing we know, so we can consider, for example, the S12 pole. So as S12 goes to 0, we're going to have a pole. And we know that the residue of this pole is going to be equal to the product of two 3-point amplitudes. So let me remind you of the 3-point amplitude that we wrote. So we said that M of 1A minus, 2B minus, and 3C plus, for example, is equal to some G, FABC, 1, 3 cubed divided by 2, 1, 2, 3. And the thing that we saw last time is that this thing is anti-symmetric under the exchange of A, B, and C. Okay, so we'll need to multiply 2 of these guys in order to get the residue of the 4-point amplitude. Okay, so what's the residue near this S12 pole? So the residue here is given by the product of these two 3-point amplitudes, where here I have 1 minus, 2 minus, with the indices A and B. And let me label this momentum by P. And let me take, so these guys are incoming, and let me take this as incoming too. So P is equal to minus P1 minus P2, and it's also equal to P3 plus P4. And then on this side, I have minus P coming in, and we have 3 and 4, and this was C with plus and D with plus. So we need to take the product of these two amplitudes. So the residue is of the form G squared FE AB FE CD. And then we have actually, so the residue itself is this. I'm just multiplying the two amplitudes here times 4, 3 cubed divided by minus P3 and minus P4. 4. Okay, so that's the residue. And so my naive guess for the amplitude then is that it's going to have this form near S12 equals 0. Okay, and so now I have this minus p appearing here, which is going to cost me a minus sign, turns out, but it appears twice, so it doesn't matter. And we can massage this thing a little bit, so let me do that. So for example, one thing that I can write here, let me first of all write the whole thing is S12 times 1, 2 cubed, 4, 3 cubed. And then I want to write 1p and bring in this p4. So I can write this as, let me write it bigger, 1p4. And then I have this 2p and 3. So this is 2p3. And now I can play with this a little bit. So I can take the 1p4 and I can use the fact that p is equal to 3 plus 4. Now, the 4 here is not going to contribute because acting on the 4, it gives me 0. So I'm just left with 1, 3 times 3, 4. And similarly, I can do the same thing for the other factor that I have in the denominator. And I can write the whole thing as 1, 2 squared, 3, 4 squared divided by S12, S13. So you see that it doesn't look very good because this looks like a double pole. And this was clear sort of from the very beginning because we looked at the S12 pole and the residue there was this combination. But these 3 points have all these funny singularities. They have all these spinor products in the denominator. So they don't look local at all. They look quite non-local. And therefore, we get this double pole. Okay? So this doesn't look good. And again, it's related to the fact that the dimension of this thing here was minus 4. And the fact that these 3 points are very non-local. Okay, so let's look at this a little more closely. So let's try to write down a more general ansatz for this function fabcd. So near this S12 pole, I can write it like this, S12, S13, which takes care of the dimension, times some f tilde ABCD, which is dimensionless. And since this is just a 3 amplitude, the only thing that can appear here are things like S12 divided by S13, because I need something dimensionless. So in principle, I can write an expansion in these guys. But of course, the thing to note here is that you can't have powers of the Sij's that are too negative, because we know that the worst thing we can have is a single particle pole. We can certainly not have things that have worse poles than this. So this tells you that the first thing that can appear here is just a constant. And then that's basically it. Otherwise, you're going to get poles that are way too singular. So using this, we can now write a general ansatz. for the amplitude. And this ansatz is the following. We can have this, and then there's some A1 divided by S12, S13, plus A2 divided by S12, S23, plus A3 divided by S13, S23. And that's sort of the general thing that we can have. And now we can look at the pole structure again. And let's again start from the S12 pole. So S12 goes to 0. So when S12 goes to 0, we have that S13 equals minus S23. And then you see that what we have two terms there with S12 in the denominator. And the two terms appear with the opposite sign because one of them has an S13 and one of them has an S23. So altogether, what the S12 pole tells us is that A1 minus A2 has to be equal to G squared times FABE FCDE. Okay, so now we are basically isolating the S12 residue, and it needs to be, so that fixes A1 minus A2 to be given by this. Similarly, we can do the same thing for the other guys. We can look at the S13 pole and the S23 pole. And because we only have three objects appearing here, A1, A2, A3, when we add up these equations, we'll get some constraint. And the constraint we get is precisely the Jacobi identity. So collecting these three equations, we have that ABE, FCDE, plus FACE, FBDE, plus the remaining permutation. That thing adds to 0. So this is the thing that we promised from the beginning, requiring that this 4-point amplitude has the right structure, as a consistent structure, that is requiring that it has just single particle poles, and at each one of these single particle poles, the residue is given by the product of two 3-points. We get this relation that the constants that these tensors need to satisfy, and this is the Jacobi identity. And you see that it's sort of non-trivial. It comes from the special form of this 4-point amplitude, and the fact that we have these things a priori, it seems that we have these things that look like double poles, but they cannot be there. So at this point, we understand that the interactions of spin 1 massless particles are really governed by Lie groups. Okay, the 3 points are proportional to the structure constants that are completely antisymmetric, and the structure constants obey the Jacobi identity. So this is the sort of brute force construction of this amplitude. Okay, so let me remind you what we invoked here. Sure. if you, you can talk about it this way. Yeah, you can phrase it this way. In other words, if I have a spin 1 particle that's self-interacting, then it has to be what we call a gauge boson. Yeah, it's associated with, so yeah, so let me say two things about this. I mean, so you see that, okay, let me say a few things. So first of all, we see that there has to be at least n of these guys, at least 3 of these guys, right? So there cannot be a single one. This is something that we already saw yesterday. And we see that the structure is governed by some Lie group, okay? And what we're seeing here is sort of the global part, okay? Because we have an amplitude, and the amplitude is controlled by the Lie group, and therefore it's proportional to the structure constant and so on and so forth. And if you wish, this is just the global part of the symmetry. When we talk about particles, because we're talking about particles here, we're not saying the local symmetry, okay? The local symmetry is kind of an artifact. The local symmetry is something that comes in when you talk about the Lagrangian and you talk about fields. But the physical thing is the global symmetry, okay? But in order to have the local symmetry, I have to have the global symmetry. And because the local symmetry is not physical, the global symmetry is. So of course, all my amplitudes should respect all the global symmetry in the problem. Okay. Sure.
So one other example for vectors would be vector mesons.
Yes.
Is this proving that vector mesons must obey or must have a Jacobi identity? Or does it mean is it a proof that they cannot be massless?
Okay. So, right. So this is, here they're massless. We can come back to talk about massive things too. And here notice that this G here is dimensionless. Okay, so this is so the gauge coupling is of that form. For the vector mesons, there are other, and also for these guys, there are other things that I can write down that are sort of non-renormalizable, and we can write them down. So you can ask me this question again when I'm talking about massive things, but yes, if there was a part that was a dimensionless part, then this is what it would need to obey. Okay. At this point, we're imagining that these are indeed fundamental particles, but yes, you could sort of ask the question about composites too. Okay, so let me just remind you what we invoked here. So the first thing that we invoked was the little group, namely Lorentz. The other thing that we used was spin statistics. And the final thing that we used was the factorization. And in particular, the fact that we just have single particle simple poles in the tree amplitude. Okay. So what about more terms? And this is kind of coming back to your question. So as we already said yesterday, even at the level of the 3 points, we can write more terms. So there are more terms that we can write down also for the 4 point. So the little group part, I have no choice. It has to be this thing here. Remember what I said was I can have here these two things in order to soak up the dimensions. And then I have to have something that can only involve powers of these guys, because this is, I need to construct something that's dimension minus 4. So this is assuming that there's no scale in the problem, because these guys are massless and there's nothing else that I can write down. But if I do have another scale, suppose this is some effective theory, and then I have some cutoff scale lambda. In this case, there's certainly more stuff that I can write down. So I can write down some 1 over lambda to the 4th times some polynomial in these S12 over lambda squared and S13 over lambda squared. So these things are certainly there, okay? And we expect them to be there in any EFT. These would be precisely the contact terms corresponding to some EFT operators. And this is something that we're going to use very heavily tomorrow. But as I said, this is already something that we saw, because what are we doing here? We're just constructing the most general amplitude from the bottom up. So of course, we're going to get these terms too if we have another scale in the problem. Now, these have nothing to do with the factorization, because they're completely local. They don't have any poles associated with them. So they're not spoiling the construction that we had before. They're completely independent of that.
So I have one question about this. So in the, you already mentioned about 4.4 gluon scattering amplitude, right? So in the usual Feynman diagram approach, there are 4 diagrams,
Yeah. So
including contact interaction. But here now, if you bring this lambda to the infinity, it disappears.
Right. So actually, so this is my next point. Very good. Thank you. So that's the next thing I want to talk about. So you can ask exactly this question. You can say, suppose that we calculate this using Feynman diagrams. So with Feynman diagrams, I also need to include this 4-gluon interaction, or 4-gluon vertex. So it goes like g squared and 2 powers of f, and it is a very complicated object, and you know it's there. So what about it? I mean, here it seems that I didn't need to think about it at all, right? We just talked about the 3-point amplitudes, which only know about the 3-gluon vertex. So how come we don't need this? And so, so let's talk about that for a second. So in order to answer this question, I want to give you a little exercise. But let me wait with this exercise for just a second. Okay, so so again, I was able to calculate stuff without any reference to this vertex. And the point is that it's something that shouldn't surprise us too much. Because remember, this vertex is completely dictated by the gauge invariance, right? The gauge symmetry tells me exactly what this coupling is. I don't have any freedom in this vertex. It's entirely determined by the gauge symmetry. So this vertex should not be, it is not an independent input in our theory. So it's not surprising that I could get away without talking about it at all. Okay? The symmetry, the construction here, if you insist on Lorentz and the other properties that we talked about, you get the gauge symmetry for free. Okay? So it's not surprising that we didn't need to talk about it. But there is more to the story. So let me come back to that in a second. But already at this point, we can say this is a very different object. This foreglown vertex is very different from those things that I can add here, because these things are new interactions. These are some new EFT contributions. They have nothing to do with the essential gauge coupling that I started from. So these are really new independent inputs in the theory. And so I cannot hope to get them from the 3 points, and I just need to add them by hand. Okay? So this is always going to be the story. Basically, for any endpoint amplitude, we can always add new endpoint contact terms corresponding to operators within external fields. And the lower point things only contribute to the factorizable parts of the amplitude. Okay. So now there is one more tool that I want to mention, which is kind of practical and also related to the structure that we've been discussing, which is something called color ordering. So now remember that we already know that we're dealing with a gauge theory, okay? At this point, we know that the F's are really structure constants. So we know that we have some gauge symmetry. And we know that the FABCs are structure constants of the relevant Lie group. And so the idea of color ordering is very old. There's actually a very useful review that describes it by Mangano and Park that's very, very old. And it also contains lots of useful identities for color structures and the cross-section. So that's a nice place to read about this. So the idea is the following. We can always write FABC as minus I over square root of 2 trace TA TB TC minus trace TA TC TB. And once you use this identity, you can write down your amplitudes in the following way. So suppose we have some n gluon amplitude. And gluons here can be any gauge bosons, of course. So AN3 can be written as G to the n minus 2, sum over non-cyclic permutations, trace TA sigma 1 to TA sigma n, AN3 of sigma 1 to sigma n. So essentially, I can organize the amplitude in terms of the different traces with the different orderings of the generators. Each one of them is multiplied by something. And because these things are orthogonal to leading order in n, the reason this is useful is that each one of these sub-amplitudes here is gauge invariant. Okay, so we can compute each one of them separately. And this is very nice because it just tells you that in each one of these amplitudes, the gluons have a certain ordering. So for example, if I'm calculating the coefficient of trace TA1 to TAN, that would involve the gluons 1, 2, 3, up to N. Okay? So only indices that are adjacent here can be adjacent in the amplitude. And the reason why this is very useful is that it separates the different factorization channels. So for example, in this amplitude, I can have an S12 pole because I can have something like this. But I don't have an S13 pole because 1 and 3 are never next to each other. Okay? So not all the poles can appear together. The different, in each one of these amplitudes, I'm only allowed to have a subset of the factorization channels, but not all of them. And this would also help to disentangle the computation that we did before. Before we were looking at a 4-point amplitude without worrying about color ordering. So of course, all the orderings enter and we get a big mess. But if we work in this way, it makes things a lot simpler. Okay, so what I want you to, the exercise that I want you to do now is the following. So the question we're asking is, why doesn't this guy contribute? So what I want you to do as an exercise is to show, so again, let's consider the 4-point amplitude. So we have a 4-gluon amplitude. The one that we talked about before. So I have M 1 minus 2 minus 3 plus 4 plus. And I want you to show that you can always choose the reference momenta for the polarization vectors for the epsilon mu's such that this vertex always vanishes. So this is a normal Feynman diagram computation. You just do the Feynman diagram computation and you look at this particular vertex and you can show that you can always choose your polarization vectors, in practice the reference momenta for these guys, such that the 4-gluon vertex never contributes. And this is why we didn't have to use it. Okay, so that's the answer to the question. And you see that this is related to gauge invariance, right? The reason that I have the freedom to choose the epsilon mu's in various ways is related to the gauge freedom. And that guarantees that this thing doesn't contribute. So you see that it's really, it's not independent. It's not an independent input from the 3 points. And that's why we didn't need to use it. Now, I think 2 days ago, someone asked me, maybe you did, about phi to the 4th. So we were talking about 3 points, and you asked me about the phi to the 4th coupling. So when I consider a scalar theory, we showed that the 3 scalar amplitude vanishes for a massless particle. But then there's also phi to the 4th. So phi to the 4th, I can write some lambda to phi to the 4th in the Lagrangian, and then I have a lambda here. And that guy is there at the 4-point level. But you see that it's very different from the story with the gluons because there's no symmetry that controls this, right? So that's an independent coupling and it will appear, but it has nothing to do with the 3 points and it's completely local. There are no poles here. Okay, so it's not like it's related to something of this type. In this case, both of these guys vanishes. Both of these guys vanish. Okay, any questions about this? If we go to higher point amplitudes, then we'll, so for example, the 5-point amplitude is going to factorize also in a 3-point amplitude and a 2-point amplitude.
So, but in this case, should I include the 4-point?
Yes, right. So the 5-point amplitude, so here is this vertex. Now I have a 5-point amplitude. And you see that the 5-point amplitude can factorize on this. Yeah. So these are always, everything that I write down up to a certain point is an input to the higher point amplitudes. And I can get those by factorizing on these lower point things. More questions?
Maximum building block?
No. You know, you can go up and up and up. Let me just give you an example. So actually the next trick that I'm going to discuss is something that allowed people to calculate all the n gluon tree level amplitudes, okay, for any n for QCD.
Means if we can just by trying to cut all the complex vertices, then as you show me in the figure, just what I wonder is that 4-point is the 4-point amplitude is the maximum building block. I mean something. So you showed us the 5, 4.
Mm-hmm.
Yeah, cannot be factorized. Yeah, cannot be factorized. Yeah.
In this case, yeah. Mm-hmm.
But in general case, there are something cannot be factorized.
Exactly, yeah. That in this case too, right? So yeah, so you know, I can write down some EFT operator that involves 10 fields. Okay, so the first time it's going to contribute is when I calculate the 10-point amplitude involving that. But let's wait with that and come back to that when we talk about EFTs. Okay, we will actually do that. Okay. Okay, so the next thing I want to talk about is recursion relations. So let me explain what we mean by that. Okay, so, okay, or maybe recursion relations and momentum shifts. Okay, so what we said is that we can sort of bootstrap the amplitudes. That is, we start from the 3 points, and then we can construct the 4 points by knowing how they factorize on the 3 points. And in principle, we can go on and on and on in this way. But one thing that I told you already yesterday is that what are we using here? The thing that we're using is the analytic structure of the amplitude. But this is a function of many variables. So it's a complicated problem, right? It's not easy. So the idea here is to sort of turn the problem into a problem that depends on a single variable, a single complex variable. Now, this more brute force bootstrap was used very early on to calculate QCD amplitudes, but these tricks of the trick of using momentum shift was discovered by BCFW in 2005, I guess. Okay, so yes, and this is Brito, Cacciazzo, Feng, and Witten in 2005. Okay, and the nice thing about this is that it allows you to get closed recursion relations and in some cases obtain closed forms for endpoint amplitudes. Okay, so let me describe to you how that works. So this is the idea. Suppose we are interested in an amplitude with some P1 to Pn. Then we can do the following thing. We can take each one of the momenta, Pi, and shift it to some headed momentum, but which is given by the original Pi plus Z times some 4-vector R. Now, in order for this to be a viable amplitude, in terms of the shifted momenta, I want a few things. First of all, I want that the sum over Ri is going to be 0, just so we still have momentum conservation. We want Ri dot Rj to vanish, and we want Pi dot Ri to be equal to 0 for all Ri. So this is not a sum, this is for each one of the i's. Provided that we have all these, then these guys are light-like, we have momentum conservation, and we can think about the amplitude in terms of the shifted momenta as an on-shell amplitude. Now, in principle, we can make any number of shifts here, right? Because I can choose this R in many, many ways. And typically what you do is you don't necessarily shift all the momenta, you just shift some of the momenta. And not only that, but remember that we said that each momentum here I can write as I, right? I can write it in terms of massless spinors. So I can also choose to shift just this guy or just this guy. Okay, so I can take, for example, I to I. Okay, this is not enough space. Okay, let me write it over here. So I can take, for example, just some I to I plus Z times some Ri, or I can take some J to J plus Z Rj, and just do this for a subset of the I's or the J's. So these are called sometimes holomorphic and anti-holomorphic shifts because it's just the holomorphic or anti-holomorphic spinors that change. And what kind of shift you want to do is something that you need to determine on a case-by-case basis. Different shifts are going to work for different problems. Okay, but that's the idea. Okay, so let's consider now the headed amplitude, the shifted amplitude. And so now we have this an hat, which is a function of Z. And this is the reason we did this, is that we just have it written in terms of a single complex variable. And it only has simple poles in this Z. Okay. Now, where do the poles come from? The poles come from, of course, the usual story when we have some pi squared, which is given by, let me call it, so it's some pij, where I have pi plus pj, some number of shifted momenta that vanish. So here is, let me draw this over here. So here is the amplitude. There is some I here, I plus 1, all the way up to j. And here there's the rest of them. And this is this pij hat. So the hats just stand for the fact that the legs can be shifted. And this guy is the sum of all these incoming momenta. And we know that the residue, in this case, is going to be equal to AL. Let me wait for a second before I write this. But we know that the residue is going to be equal to the product of this guy times this guy. Okay, so the pole is coming from the instances that this p squared is going to be 0. Of course, in some cases, if this pij doesn't depend on z, because I didn't shift any of the relevant momentum, then it's not going to lead to a z pole, but otherwise it does. And where's the location of the pole? The pole is going to be at z, which is equal to zij, which is given by minus 1/2 pij squared divided by pij dot rij. And this rij is coming from the total shift here. So my pij, I can write as pi plus pj plus all the shifts, z times ri plus rj. So this is the pij, and this over here is what I'm calling rij. Okay, and again, in order to have a z-pole, what we need to have is that this rij, big rij, is non-zero, and then the location of the pole is simply when this whole thing squared vanishes, and you can solve that and find that this is the zij. This is the location of the pole. Okay, so now working near this pole, we can write down the amplitude. We know that the amplitude is going to be equal to the amplitude on the left. It's z equals zij times 1 over pij squared times ar. It's z equals zij. And this here is the left amplitude, and this here is the right amplitude. Okay. Now we can simplify this object here. So this guy is going to be Pij squared plus 2z Pij dot Rij. And I can massage it just a little more. And there's nothing, I mean, it's all very simple algebra. There's nothing fancy here. So I can also write this propagator as 1 over 2 Pij dot Rij times 1 over z plus Pij squared divided by 2 Pij dot Rij. And finally, we can write it as minus Zij over Pij squared divided by 1 over z minus Dij. So this is homework. If it's hard to see right away, just work through it. It's very simple stuff. But this is the result that we really wanted, because now it's written in a way that makes it very clear where the poles are and what the total residue is. So now we see that the residue of a hat of z at z equals Zij is this whole prefactor. It's minus Zij times Al hat z times 1 over Pij squared Arz at z equals Zij. And at this point, we know all the residues, we know all the poles, so we can write down a closed expression for the amplitude. Okay, so what is the original amplitude? The amplitude that we're really interested in is the amplitude at z equals 0, right? So it's the amplitude before the shift. So it's the one at z equals 0. And we can write that as 1 over 2 pi I a hat of z divided by z dz. So here we just use Cauchy's theorem, and this is going to give us precisely a at z equals 0. But now we can deform this integral. So this is working in the z plane, and we have this residue at 0, which is the amplitude that we want, and we're integrating over this contour. But we can now deform the contour and pick up all the other residues. So we can write this as the sum over all the poles, the residue of A at Zij divided by Zij. And that's really sort of the end of the story. So substituting the things that we had before for all these residues over there, what we find is that we can write this as minus the sum over all the poles in A hat, Al hat, Zij, 1 over Pij squared, Ar Zij. Okay. And the nice thing about this is that each one of these poles corresponds to a particular factorization channel. So one thing that this trick allows you to do is kind of separate the different factorization channels so that they sort of don't lie on top of each other like we had in the example that we did before. Okay. So this is very satisfying because you now have a closed form in order to, that allows you to obtain all the amplitudes recursively. There is one important thing that we assumed here. Remember, we have to deform the contour from here to include all these poles over here. So we also had to close some of the contour at infinity. So what we're really assuming here is that AZ goes to infinity fast enough when Z goes to infinity. So the amplitude needs to be well behaved at infinity. And this is where these different shifts really help you, because depending on the form of the amplitude, you can choose the shift in, you can choose to shift the momenta in a certain way such that you may be able to get this form. And of course, I don't mean infinity. That would be very funny if that was the case. I mean 0. Okay, so now that it's not that easy to see, you know, and it's not easy to prove that a certain shift is going to give you the right thing. But you know, as usual in physics, if something needs to work, then it will work, right? I mean, that's the beauty of physics. So I don't want to do any explicit example because it's going to take us too much time, and I don't want to spend so much time on this. But as I said, it allowed people to derive closed expressions for all the n-gluon amplitudes in Young-Mills theories at tree level. And it's something that's theoretically very nice. Okay, good. So we're done with that. And of course, you know, as with most beautiful things, it's not like it can be always generalized to all cases of interest, right? So I think it's important to know that this thing exists, but it's not like it's always applicable. Okay, any questions about this before we go on? Okay, so if you're puzzled about the little details, I suggest that you go over it, and then if you have questions, then come and talk to me about it. Okay. Good. And so with this kind of concludes everything I wanted to say about about massless amplitudes. And the one thing I was going to do, depending on time, but I don't think we'll have time for that, is to talk about loop amplitudes. Okay, so far we just talked about tree stuff. If we see that we have time at the very end, we may talk about it, but probably that's not going to happen. But it's good to know, but let me just say one word about this anyway, because, you know, it's useful to know what we're missing too, in case you want to study it on your own. So we looked at what we really used here is the factorization of the tree amplitudes, and the fact that the tree amplitudes have simple poles that correspond to one particle poles. So it's always something of this type, just like we had before. Of course, when we go to the loop level, things start to be more interesting. And in particular, we have cuts. And so you know that loop amplitudes can have imaginary cuts that corresponds to cutting them like this. And so it tells you that just like we did here, if I want to determine some loop amplitude, what I can very often do is to say, I know that the imaginary cut has to correspond to this amplitude on the left times this amplitude on the right. So that determines the form of the cut. And from that, I can, in some cases, infer the amplitude. And so again, it's sort of the same story where you determine a higher point amplitude or higher order amplitude based on lower order amplitudes. Now, people actually took this a few steps further and introduced something called generalized unitarity. Again, this goes back to work by Byrne, Dixon, Kosower, Dunbar, I think, in the 90s. So what these guys said is, why stop at this kind of cut? Let's even imagine cutting the amplitude in more than one way and extracting all the information that we can out of that. And I'm not going to have time to talk about that, but this is something that you can use in particular in order to infer the singularities that come up in the amplitudes. And this is something that's useful if you're interested in anomalous dimensions and running. These are the relevant things to look at. So if you're interested in this, I can tell you, you can ask me and I can tell you a little more where to look for this. Okay. But in the remainder of the lectures, I want to start talking about massive amplitudes. And, to some extent, I mean, the whole story I'm telling you here is that we want to stick to the physical degrees of freedom. And we want to talk about particles. And the particles that we know are, of course, some of them are massless, but many of them are massive. So if we want to talk about real physics, we should talk about masses too. And in particular, if we're interested in the Higgs mechanism, then it's all about mass. So I certainly want to talk about massive particles like the Higgs itself, the W's, the Z, the top, and so on and so forth. Or if I'm interested in low energy stuff in the chiral Lagrangian, I want to talk about masses. So for many physical purposes, I really want to talk about masses. Okay, so we're now going to turn to massive amplitudes, and I want to do two things. One is I want to talk about bottom-up constructions and rediscover some of the standard model things that we know. And then I'm going to talk about EFT applications. Okay, good. And we'll see that somewhat surprisingly, the massive amplitudes in some sense are nicer to work with than the massless amplitudes. So we'll see that in a second. Okay. So what's the plan? The plan is, the first thing I want to do is I want to talk about 3 points. And then I want to talk about how to go on to 4 points and so on and so forth. And this is going to be the main difference. This is going to be where this is going to be simpler than the massless case, because essentially when you talk about the 3 points, the massless 3 points were sort of non-local. they had all these negative factors of the spinor products in the denominator. But now that we go to massive amplitudes, they're going to be much nicer. They're going to be local. Everything is going to be up in the numerator, and so that's going to make things much easier. And it's not terribly surprising because in some sense you expect the mass to smooth away all the singularities. So the massive amplitudes are smoother in some sense than the massless ones. Okay, good. So let's start. Okay, now there's one, so before we start, there's one sort of general thing that I want to say. So we already used some of the properties of amplitudes in order to construct them from the bottom up. But there's another element that I haven't talked about so far, which is sort of the high energy behavior of the amplitudes. And of course, when I'm talking about some massive amplitude, and I'm talking about the high energy limit of that, that's going to turn into some massless amplitude. It's the same thing whether you're taking the high energy limit or you're taking the massless limit, essentially, right? It's really the same. So one thing that we know about amplitudes at high energies is that the S matrix, but because we want the S matrix to be unitary, what we know is that the cross section has to fall fast enough with the energy. So the cross section always has to fall with the energy, and it has to fall fast enough. Otherwise, we're losing the notion of probability, right? We get cross sections that are that break that give us probabilities that are sort of larger than 1. So if we're interested in tree amplitudes, and specifically 4-point tree amplitudes, the thing that we know, and this is the thing that's going to be very useful to consider, is the fact that for high energies, our amplitude should only scale as e to the 0. It should only scale as e to the 0 because the cross section should fall something like 1 over e squared. So in particular, if we find that this A4 contains terms that are some power of n where n is larger than 0, then that means that the theory has some cutoff. Okay, this cannot happen in a theory without a cutoff. So that means that, first of all, we have some cutoff lambda, and secondly, any such power should appear suppressed by lambda. So these sorts of terms that are suppressed by the cutoff are okay, but anytime you see an amplitude that rises with a higher power than 0, then it signals that the theory needs to be cut off at some point. Okay, and this thing can be referred to as the requirement of perturbative unitarity. That is, we calculate the amplitudes, and the cross-section is perturbative, and is unitary only as long as we have no powers of E that are positive. So this is something that we're going to invoke. Okay. Now, in particular, if we talk about the standard model, so as we said, in the standard model, we have particles of both, particles that are both massless and massive. But in the case of the standard model, we know that if we were to extrapolate the standard model to high energies, the only way to do that is so starting with the, so suppose I'm not, so the question is, what do you mean by the standard model? Okay, so usually what we mean by the standard model is the SU3 times SU2 times U1 Lagrangian. But let's suppose that I'm taking just the standard model particles and their interactions. So the standard model particles are the physical particles. I have the gamma, the W, the Z, all the different fermions. I'm not going to write them all down. And you can ask the question, suppose we extrapolate these interactions to very high energies. What's going to happen? Okay? So if we do nothing, and certainly before the Higgs was discovered, suppose we didn't even know that the Higgs was in the game. So we know that if we extrapolate these things to high energies, the only way to do this consistently, such that the theory maintains perturbative unitarity, is if you indeed have the gauge symmetry of the standard model, SU3 times SU2 times U1. And in particular, you need the Higgs, of course, in order to complete the story and have this picture with the full standard model gauge theory. So this is something that was known from the 70s. There are many authors who worked on this. There's Llewellyn Smith. There is Lee, Quigg, and Thacker, and a whole list of other people. And what these people showed is that the standard model, namely the SU3 times SU2 times U1 theory, is the only theory with perturbative unitarity that you can get by extending the interactions of the standard model particles. So this is something that's actually very easy to see when you work with on-shell amplitudes. So there's nothing really new here, but it's just much easier to see when you work with amplitudes compared to the things that were used back in the 70s. So it should be no surprise if you start from on-shell amplitudes and require that you have perturbative unitarity, that you recover the Higgs mechanism and everything that comes with it. Okay, and this is actually one of the things that we're going to see. Now, of course, it doesn't mean that we cannot have new interactions. We can have new interactions in the theory, but these interactions need to be down by some cutoff. So anytime, just like we said before, anytime we have some e to the n behavior, where this n is larger than 0, it should come with the appropriate power of lambda, where lambda is the cutoff of the theory. Okay, so this is going to be the sort of big picture of what we can expect to see. And now let's start to see that. And again, the first example that I want to start from is the same thing that I started from before, namely the example of 3 spin 1, or I should say the 3-point amplitude of spin 1 particles. And now I want to take their mass to be non-zero. And of course, in the standard model, I do have an example of this type. I can write down a coupling of a W plus, W minus, and a Z. And in this case, it's even something that I could sort of analytically continue to something that's physical if I imagine that the Z mass is larger than 2 times the W mass, then this would even be a physical amplitude. So I can write this in this limit, and then, of course, take the masses to be what they really are. Okay, so suppose I want to construct this amplitude. Now this is a 3-point massive amplitude. So we know the rules for that. So the rules are that because all these guys are spin 1s, let me denote them by 1a, 2b, 3c. And let me use underlines to indicate that all of these momenta are massive momenta. So now I need 2 spinners for each of them. So basically, I can construct the amplitude by having either angle brackets or square brackets involving 1, 2, and 3. And that's really all that you can have in the story, because suppose, for example, that you had something like 1, 2, 3. So then I can use momentum conservation and write this 2 as minus 1 plus 3 using momentum conservation. And then with this one so this one is acting on this guy here and giving me minus M1, M1, 1, 3. And then this guy is acting on this side, and it's giving me M3, 1, 3. And you see that I can reduce this guy to just a simple product like this. So these things are the building blocks that I can use to write the most general amplitude. And so in principle, just doing the counting, you see that a priori there's 8 different combinations of these guys that you can take, but you can show that there's one identity that relates them, and there's actually only 7 independent terms. Now, I'm not going to write to you all these 7 independent terms on the board, because it's a little too much. But instead, let's consider the limit that these 3 guys are degenerate. So let's imagine for a second that MZ is the same as MW. So we have 3 degenerate things of the same mass. And it's actually not such a bad approximation. So in this case, I have a pretty simple expression to for my amplitude. So first of all, I can write this thing over m squared. So m is the mass. And then I have this combination 1, 2, 1, 3, 2, 3, plus all the different permutations of these guys. And then I have another thing, C prime ABC over lambda squared times 1, 2, 1, 3, 2, 3. And again, all these guys are underlined. And I also have this another term here where the angles are exchanged with the squares are exchanged into angles. So this is the most general thing I can write down. And let me also stick a G here in front of this guy. Okay, so let's now look at this creature. So the first thing that you can convince yourself of is that both of these kinematic structures, the one that appears here and the one that appears here, both of these are completely anti-symmetric with respect to exchange of AB of 1, 2, and 3, just like we did in the massless case. And actually, in this case, in the massive case, it's even easier to see because everything is sitting up on top, so the anti-symmetry is very easy to see. So we conclude again that CABC and also C prime ABC are fully anti-symmetric. And you see that this is something that we can see already at the massive level. So already at the massive level, we see that if we're talking about self-interacting things, we have to have at least 3 of them, which is exactly what we have in the standard model, because we have the SU2 that has 3 gauge bosons. But that's the minimal number that we have. And we're starting to see that these are the structure constants of the Lie group. So that's the first thing that we see. In this case, because in the standard model, we really have n equals to 3, then we can always normalize these guys to be some number times epsilon ABC. And the same thing is true for the C prime. So both of these guys are proportional to the SU2 structure constants. Okay. Now, I chose a very particular normalization with 1 over m squared on top and 1 over lambda squared in the bottom. And the reason I did that is based on the high energy behavior of the amplitude. So let's talk about that for a second. So now we're talking about the high energy behavior. And let's do it in the following way. So since we're talking about 3-point amplitudes, remember their dimension is 1. So at high energy, or for 0 masses, I expect the amplitude to go like E. Now, we also said that in the 3-point massless kinematics, we could either have squares or angles, but not both. Okay? So you see what happens. As we take the high energy limit, either the square is non-zero or the bracket is non-zero. So essentially what's going to happen is that if this is the case, then my angles are order E. And these guys here are order m squared over E. So based on this, we see that the term that I have on top has, for example, 2 angles and 1 square. So if I divide it by m squared, it's going to give me something that indeed goes like OE in the massless limit. On the other hand, in this second structure, I have either 3 squares or 3 angles. These just go to the same thing in the high energy limit, and I need to normalize them with the lambda squared. In other words, at high energies, one of them is going to go like E cubed, and therefore it has to come with a lambda squared. Now, essentially what I'm invoking here is perturbative unitarity. So you can ask the question, let me just take 3 more minutes. You can ask the question, what do I really mean by the high energy limit when I'm talking about 3 points? In 3 points, there is no high energy limit. If this is a physical amplitude and I have a z going to 2 w's, if I have enough, if the z is sufficiently massive, then the highest energy in the game is the z mass, right? But again, the trick is that we're going into complex momenta. In complex momenta, we can talk about the leading behavior of the momentum, and that defines our high energy limit. And then I can ask questions about perturbative unitarity. So the thing that really exhibits perturbative unitarity is the 4-point, because that's really the first physical thing that we have. But the 4-point, you know, is essentially made of 3 points. I can think about it as gluing 2 3 points together. So I have an A3 times another A3 times the propagator, and the propagator goes like 1 over E squared. So if this guy goes like E, and this guy goes like E, then altogether I get something that satisfies perturbative unitarity because it's E to the 0. But if I have any higher power here, it should come suppressed with the lambda. So that's how I determine the normalization of the different terms. Okay. So I think this is essentially where we're going to stop. And it's almost everything that I wanted to do. The one thing that I wanted to do and we didn't finish is to look at the amplitude with 2 fermions, the fermion vector coupling. So this is the first thing we're going to start with tomorrow. Okay, thank you. Any questions? Okay, thank you. So yes, this is indeed the last lecture, but you can feel free to ask me questions throughout the rest of the day. So what we're going to do today is to finish talking about massive amplitudes, the relation between massless and massive, and EFT applications. And I just wrote down here, so we started talking about massive amplitudes yesterday, but I want to remind you some of the things that we said a few lectures ago, which seems like a long time. Seems like a long time to me, so I'm sure it seems like a long time to you. So just to remind you, we write a massive momentum as the sum of 2 light-like momenta. And so we can label these guys with I running over 1 and 2. the dot product of them is equal to m squared. And this is what the Dirac equation turns into. All my notations are from this paper. And, you know, there are many places to make mistakes here. So if you want to get the real thing, it's in this paper here. And these guys, the angles and the square spinners are rotated by these little group SU2 matrices. And we know how to write the polarizations. So these are the polarizations for the massive fermions. And this is the polarization vector for the spin 1 field or the spin 1 particle. And remember that I use this underline notation, which is really meant to be bold, but I can't bold everything on the board. So I'm using underlines. This is this notation introduced by Arkani, Hamed, and Huang. And what it really means is that I'm hiding the indices on the p's here. I'm hiding the little group indices, and I symmetrize over them. So that's what the notation means. Okay, so the thing that we did yesterday was just the first stage. We're trying to construct amplitudes from the bottom up. And so we looked at a particular 3-point amplitude, namely the massive 3-point amplitude for 3 spin 1 particles. But let me now emphasize an important advantage of this formalism. So one advantage of this formalism that we already discussed is that it's covariant under the little group. We can see the little group properties of everything very clearly. And another nice feature is that there is a very simple connection between massless and massive amplitudes. And so that's the first thing I want to talk about now. In other words, if we take the high energy limit of the massive amplitude, it's really simple to see the limit. So let me write my light-like vectors like this. So I'm splitting P into 2 light-like vectors. And I can always choose to work such that in the high energy limit, so now I'm going to talk about high energy. So M is much smaller than E. So this guy can be OE. And then this guy is order M squared over E. And once we do this, once we make this choice, then only one of these guys survives. So for example, the PI with I equals 1 here is roughly of order square root of E. But the other guy, P with I equals 2, is roughly M over square root of E. And for the angle spinners, it's the other way around. So this angle spinner with I equals 2. Question? Here? This is a spinner, so it has to be dimension 1/2.
No. This moment.
Yeah, this is so remember the if
I see,
have
I see.
IJ,
Okay.
that's dimension 1.
Oh, okay.
Okay, so a spinner
Yeah,
is
yeah.
1/2.
Yeah. Thanks.
Yeah, good. It's yeah, it gets some getting used to. Takes some getting used to. Okay, so so for the angle spinners, it's the other way around. This guy is going to be square root of E, and this guy is going to be order M. Okay, so what this tells you is that if we look at our amplitude, so our amplitude is some tensor in little group space. So only some elements of this tensor survive in the high energy limit. So let me take one example. Let me consider an amplitude where 1 is a spin 1/2 fermion, 2 is also a fermion, 3 is a vector, and 4 is a scalar. So here is one term that I can write here. Let me actually write this one. So you see this is something that's consistent because 1 appears once, 2 appears once, and 3 appears 3 times, and 3 appears 2 times, which is fine. And what this really is, it's a tensor because I can have 1, I1, 3, I3, 2, I2, and 3, J3. This is what's really written here, where I now wrote the indices explicitly. So you see that in the high energy limit, the thing that will survive here is I1 equals 1. I2 here is 2. And I3 is 1. And J3 is 2. Okay, so there's a single component that's going to be the dominant component in the high energy limit. So in the high energy limit, what does this turn it into? It just turns into 1 with the index 1, and so on and so forth. So it's really becoming K1, K3, K2, K3. In other words, I can call this thing just 1, 3, 2, 3, where these are just the massless guys. Because remember, in the high energy limit, P and K coincide. So you see that taking the high energy limit is very simple. It simply means that you're unbolding your spinor structure. So to get the high energy limit, all we need to do is drop the bolding or drop this underline notation that I have to use on the board and just have the simple massless spinor structure. Okay? Yeah. Yeah. Okay. So oh, this one, this means symmetrization. Ij means Ij plus Ji. Yeah. More questions? Okay. So this is one reason, this is one thing that makes this formalism really nice. Okay, so now let's go on and continue the thing that we did before. So we were talking about the bottom-up construction of massive amplitude. And the first ingredient here is all the 3 points. So the first thing that you need to do is you need to write down all the 3 points. And of course, at the next stage, we can get the 4 points and so on from the 3 points. But for the 3 points, all these results are actually available. For the standard model, we derived all of them in this paper from 2019 that where I'm taking all my conventions from. And for all the 3 points in some generic theory, which is not the standard model, but with spins up to 3. We listed all of those in this paper from 2020. And yesterday we did one example. Yesterday we did the 3 spin 1 particles. And we saw in this case too how we get the structure constants. But now let me talk about another example. And that is the fermion-fermion vector amplitude. And the reason I want to talk about it is that in this case too, I want to show you how certain things that you know, in particular the Higgs mechanism, arise from a bottom-up construction. Okay, so I want to write down the most general 3-point amplitude here. And there are 4 structures that I can write down. 1, 3, 2, 3. 1, 3, 2, 3. And 1, 3, 2, 3. And 1, 3, 3. And everything, of course, is underlined. Okay, so these are 4 independent structures that I can write from these 2 momenta that have the correct little group structure. And if you want to check that that's the case, it's a nice exercise. You can convince yourself that there's nothing else that I can write here. And these guys, in principle, come with different couplings. So we can do the same sort of dimensional analysis that we did yesterday. I'm going to repeat it. And here I want to have a coefficient of the form GR over M. Let me put V here for the vector. Actually, let me just call this guy Z, so we can make contact with the standard model. So then this is MZ. And this coefficient, I want to call GL of MZ. And here I want to have CR of lambda over lambda. And here I want to have CL of lambda. And I'm putting a bar on my lambda because I want it to be it's some EFT scale, but I want to sort of distinguish it from the scale of the Smith. So this is my low energy. This is some cutoff scale that I have in my low energy theory. Okay, so now the question is, how do I know whether to put an M downstairs or a lambda bar? So let me tell you how I know that. Okay, so first I'm just going to give you a rule that doesn't seem terribly motivated, but it works. So the rule is that if have a vector that appears with a P and a P, namely 1 angle 1 squared, then it should come with 1 over M, the mass of the vector. So this is just a rule that I'm giving you. Now, how do I know that that's the case? I know that that's the case because remember, the polarization for a massive vector is normalized like this with an M. So basically, what I'm telling you is that if I normalize such factors with a 1 over M, then I can read off correctly the dimension of the operator that's associated with this term, or the dimension of the coupling. So for example, in this case, I'm telling you that here's 3 is a vector. It appears once with an angle, once with a square. So I'm telling you, it needs to come with an m in the denominator. And now, if we do dimensional analysis, remember that this is a 3-point amplitude, so it has dimension 1. Up here, I have dimension 2, because I have 2 spinor products. So the coupling that sits here is dimensionless. And this is consistent with being the gauge coupling. And what we're going to see in 2 seconds is that indeed, this is associated with the gauge coupling. Okay? Now, on the other hand, for this guy, the 3 appears with 2 squares, so I'm not putting down any m. That means that I have to have some other scale here, lambda, which is my EFT scale or the cutoff scale, and this guy is a dimensionless coefficient. Okay, so that's going to be the rule. So that's the first way to see this normalization. Now let me convince you that this is really correct. So this is the second way to see this. So now let me talk about the high energy limit of this thing. And let me take Z to be a transverse in the transverse polarization. Okay, so the transverse polarization means that the indices of 3 are either 1, 2 or 2, 1. Okay, so for example, let me look at this first term here. So what I'm going to have here, for example, is 1, 2, 3, 2, 2, 1, and 3, 1. This is my leading term, and the reason that, oops, I lost this. So this is the leading term because of what I told you, and I guess I already got rid of it. For the squares, the 1 is the leading component, and for the angles, the 2 is the leading component. Okay? So you see that this thing survives at high energies. This thing is really there. And it goes like, this vector goes like E, this vector goes like E. Sorry, did I want to? Okay, so I take it back. Okay, so I did it wrong. Let's do it right. So I want Z to be transverse. So what are the indices that I should take for transverse Z? It should be either 1, 1 or 2, 2. These are the transverse one. 1, 1 corresponds to positive polarization, 2, 2 to minus polarization, and 1, 2 plus 2, 1 correspond to 0 polarization. So if I want to take the Z to be transverse, that means that both of these guys have to be, let's say, 1, if I'm taking it to have positive polarization. So now you see this guy is order square root of E. This guy is also square root of E. This guy is now 3, 1. So it's actually down by square root of M. And this guy is 2. So that's, sorry, it's down by M. And this guy is 1, 2. So that scales as square root of E. And this guy, remember, scales like this, M over square root of E. So altogether, this whole thing goes like M. Okay, or if I collect everything together, it's of order ME. And therefore, if I have the M downstairs, then that's okay. It goes like E. because the two m's cancel out. Okay, so this is maybe a little fast because you're not used to all these different indices, but if you go over this slowly, you'll see that it's very easy. All I need to remember is that these are what the different polarizations correspond to. And the other thing is how these different spinors scale with the energy. Okay. And then there's a third way to see the same thing, which is what I mentioned already yesterday in the end of the lecture. Which is that, remember, in the massless kinematics, massless 3 points, we have either squares or angles. Okay, we don't have both of them. So if we have the squares, then this thing scales like E, and this one scales like M. Or if it's the other way around, then this scales like E, and this scales like M. So whenever here I have a mixed term that has angle times square, it has to be down by M. And so if I have an M in the denominator, this is going to go like the gauge coupling, and it's going to be exactly the thing that I want. Now, of course, you can do another thing, which is to sort of think about, just take the high energy limit of this thing, and you'll see that indeed it gives you the correct high energy 3 point for a massless vector and two massless fermions. And if you want to see that, you can look at our paper on shell Higgsing. This is from 21, and we have a section there where we do all the 3 points of the toy model, and you'll see exactly how to do this exercise. Okay, so at this point, what we know is we know how all these things are normalized. Okay, so good. So now what I want to show you is that just looking at this 3 point and taking the high energy limit, we can see things that we expect based on the Higgs mechanism. So let me show you how that works. Okay. And let me just concentrate on the two renormalizable things, the things that don't have the lambda bars here. So I just want to look at this part of the amplitude, and I want to forget about these two terms here. And let's in particular choose to look at the first fermion having minus polarization, minus helicity. This guy has minus helicity, and this has a positive helicity. And then we have GR over MZ times 1, 2, 3, 1, 2, 2, 3, 1, plus GL over MZ, 1, 2, 3, 1, 2, 2, 3, 1. Okay, and if we see what happens at high energies, what this thing becomes is it becomes GL minus GR times M psi over MZ times 1, 2. Actually, is this the thing that I wanted to do? Yes, okay. But actually, I'm a little confused. I think I may have cheated. Which one do I want to do? Yeah, no, that's what I wanted. Okay, good. So I'm not working this out in any detail. You can do this as an exercise. It's a very simple exercise. So I just chose specific helicities. So this is the thing that I need to look at. And now I take the high energy limit, and you should show that in the high energy limit, this is what the amplitude becomes. Okay. This is just technical. Yes, just a sec. At this point, there is no meaning. Okay, but there is a meaning, of course. The meaning is that it has to do with, there's one component here that's going to be the leading one in the high energy limit, which corresponds to right-handed or left-handed, and so that's what this is standing for. Okay?
Sorry. Could I ask one question?
Sure, yeah.
You were doing the transverse polarization there, but if I see it correctly, if you do the longitudinal polarizations, then...
We will do that in a second. Thank you. Okay, so first I want to look at the transverse one. And remember, I'm a bottom-up person. I don't know anything about Lagrangians or Higgs mechanism or whatever. So I just look at this thing very naively. And I can ask the question, how do I take the high energy limit? For example, am I allowed to take m psi to 0 and mz such that mz is finite, or am I allowed to take mz to 0 and keep m psi finite? Are they related in some way? And you see you see right away that this thing is not well behaved because I have mz in the denominator. So for this thing to be well behaved, there are two options. So option 1 is GL equals GR. That means that my fermion is not chiral. It's a vector-like fermion. That is I have a fermion coupling to the vector, and the left coupling is equal to the right coupling. That's one option. In this case, there is no condition on the masses. The masses can be whatever they want to be. But if GL is not equal to GR, I have a fermion with chiral couplings, then m psi has to go to 0 faster than mz. Okay, so faster or the same, okay, but not slower. So I cannot take mz to 0 without taking the fermion mass to 0. So this is something that we totally expect from the Higgs mechanism. In order to take the vector mass to 0, I can take the Higgs VEV. I need to take the Higgs VEV to 0, in which case the fermion mass is going to go to 0 in exactly the same way. But I can also have a massless fermion and a massive Z simply when my fermion doesn't couple to the Higgs. If I don't have Yukawas, my fermion is going to stay massless. So again, you will see that from this bottom-up construction, and in this case requiring that the amplitudes have a well-behaved high energy limit, we recover things that we know about the Higgs mechanism. Okay. Yeah. Yeah. So,
As I know, MK and psi are given by same then if we-
precisely. Yeah.
Then if we take the BEV to be 0, then I think MG and M psi go
Yeah,
to
yeah.
0.
Right.
Yeah, proportionally.
It's
Yeah.
it's not faster. What I meant is, let me write faster or together. Okay. What I cannot have is mz goes to 0 faster than m psi. This thing is forbidden. Okay. They can go to 0 together,
Yeah.
or the fermion mass can go to 0 faster. but not
Only
together.
except the case.
Yeah.
I got it. Yeah, thank you.
Exactly. Okay. So, good. So now you asked me about the longitudinal. So let's do longitudinal. So we learned all this stuff, but now let me look at the longitudinal vector. And so for the longitudinal vector, I want to look at, let's say, 1 minus 2 plus and 3, 0. And that means that my choice of indices is different. So let me just change it over here. So now this is going to be 2. This is going to stay as 1. This is going to be 1, and this is going to be 2. These are the 2 leading contributions. And in this case, if we take the high energy limit, what we're going to see is that it's GR minus GL m psi over square root of 2 mz times 1, 2. So in this case, the one thing that we learn is that if GR is equal to GL, that is, it's a vector like fermion, then there is no coupling to longitudinal vector. Okay, so this is the one thing that I can learn from this, taking this limit. And in a few minutes, we're going to say more about this thing. Okay. So if we want to say more about the Higgs mechanism from this, we have to go to the 4-point level, and we'll do that in a second. But let me just remind you before we go on, let me say something about the 3 points. I said this before, but it's important, so I want to say it again. Okay, so for 3 points, because we're in the business of constructing all the 3 points, so for the 3 points, all the Sij's are simply m squared, the correct sum, sum mk squared, and therefore only have spinor structures. So the spinor structures are all there is in this case. And once I wrote the amplitude in terms of spinor structures, everything multiplying them are just constants, are some numbers. And so this is the full behavior of the amplitude. Okay. But now I want to go on to construct 4 points. And again, the thing that we know is that the residue of a certain pole is equal to the product of a 3-point amplitude times another 3-point amplitude. Now, in this case, because everything is massive, we don't even have the problem of seeing double poles that we saw yesterday. So remember that for the massless amplitudes, the massless 3 points, they look very non-local. But in the massive case, everything looks very nice and smooth, everything is local, and all the poles get separated. And so we can literally just glue together 3-point amplitudes and get the result. So I want to do just one example in order to demonstrate the Higgs mechanism. And so let me now look at a very similar amplitude, one with, again, 1 is a fermion, 2 is a fermion, 3 is a Z, and 4 is the Higgs. So you can get the amplitude by gluing together this one and this one. Sorry, this one and this one, where these are the fermions. This is Z, this is H. And there's also, in principle, this one. And there's also this one. But now you can show that, and this is a nice exercise, you can show that the ZHH amplitude is 0 because of the symmetry of the bosons. So this is an exercise for you. So these are the only contributions that we can have. And I'm not going to do this exercise because it's very long. But if you calculate the amplitude and then you take the high energy limit, then you find something interesting. So remember, in the high energy limit, we want to require perturbative unitarity. What that means is that if I have any terms with e to some power that's bigger than 0, they should come as e to the n over lambda n, where lambda is the cutoff. In this case, the highest energy behavior that we find is order E. And the coefficient of the order E is this thing, GL minus GR times CZZH M psi over MZ with a 2 minus Y, where this guy is just the coefficient of the psi H. It's the psi H coupling. So you see that it's the Yukawa, and this is the ZZH coupling. So this is the gauge coupling. Now, so this is the coefficient of the term that goes like E. So what do I learn? I learned that this thing has to be equal to 0 plus potentially something that's down by lambda. But at the renormalizable level, it should be, let me put an E here. At the renormalizable level, it should be 0. So what does it give you? It gives you something very nice that you should expect, which is that M psi is equal to Y times 2mz let me write it like M Z. Let me put the 2 here over C ZZH. So this is the Yukawa. This is essentially the gauge coupling. And so you see that the psi mass is proportional to the Z mass, and the coefficient is Y divided by the gauge coupling. So this is precisely what you expect. So we're seeing something very similar to the sort of thing that we saw before, namely looking at a completely on-shell construction of the amplitudes, requiring that it has all the right properties, including perturbative unitarity at high energies. We recover the relations that we expect from the standard model. So we can relearn the standard model in this way. And there's nothing surprising about this, because remember, we said that if you start from the particles that we know, and you ask, how can we extrapolate it to high energies? The only way that you can do that in a way that's, that maintains perturbative unitarity is the standard model gauge theory. Okay, so that's the first thing I wanted to say. And now let's go on and think some more about the Higgs mechanism. And you sort of see what happens from a bottom-up point of view, or the relation between high energy and low energy. So think about this example. We had this amplitude that we were looking at, and this amplitude is really, so this is the massive amplitude. We're looking in the IR, and it's some tensor in little group space, right? It has all these little group indices. And the different components of these tensor, I can take, just like we did before, we can take the vector to be a transverse vector, or we can take the vector to be a longitudinal vector. And these different components at high energies go to different massless amplitudes. And so the picture that we have is that the Higgs mechanism, what it boils down to is that the IR amplitude, let me call it IR A for amplitude, is sort of an infrared unification of different UV amplitudes. And this way of thinking of it as this infrared unification of massless amplitudes is due to Arkani Hamed et al. From this 2017 paper. Okay, so this is very nice, but I want to look at this in some more detail. And in particular, I want to do something that's similar to what we do with Lagrangians. So with Lagrangians, we have this very nice picture where we start with the massless Lagrangian in the UV. So that corresponds to the unbroken symmetry. And then we turn on the Higgs wave, and we get the massive amplitudes in the IR. And we get the massive Lagrangian in the IR corresponding to the Broken theory. And so now I want to write down some amplitude version of the same thing. So essentially the thing that we want to do is find this on-shell version of the Higgs mechanism. So this is what I'm going to call on-shell Higgsing. And this is in this paper with Ruben Galkin and Gautier Drouillet and Tepe Kitahara and my student, ex-student Yaniv Weiss from 21. Okay, so all the details of that are in this paper. So it's pretty clear how to go. So let's say that I'm interested in some amplitude with some external lines. So let's say this is some n. And I want to start from the massless theory with some unbroken symmetry. The way that I'm going to get the massive amplitude is by considering all the amplitudes that have extra Higgs legs. So I need to add a certain number of Higgs legs up to some m here. And the way that I'm going to see the massless amplitude is by taking all the Higgses to be soft. Because I want to, what does it mean that I set the Higgs to its Vev? It means that I'm sort of freezing the Higgs. It's not dynamical anymore. It's not fluctuating. So I'm taking its momentum to go to 0. So if these guys have momenta Q1, Q2, and so on and so forth, I want to take all the Qi's to 0. And this is the limit in which I'm going to get the massless amplitude. Now, in the IR, I'm going to get some amplitude where all the Higgs legs are gone. So it has n legs. Let me reverse the ordering. So this is ANIR. And it's going to be of the form V to the m times A n plus m, which is the massless amplitude that I'm starting from. Now, this V here is what we associate when we do QFT. This is the thing that we identify as the Higgs Vev. And notice that this is something that I need on dimensional grounds, because the dimension of this guy is 4 minus n, and the dimension of this amplitude is 4 minus n plus n. And so I need this scale to absorb the dimensions. Okay, so what's going to happen when we do this? So we start from this massless amplitude. We have all these extra Higgs legs, and we take them all to 0. I mean, all their momenta to 0. Okay, so the first thing that's going to happen is that all the massless spinor structures are going to become massive. That is, they're going to become bolded structure instead of unbolded structures. And we'll see how that happens. So for example, if I had some vector line, and the vector line had 2 of these spinors associated with it, these are going to become now the I equals 1 components of this massive momentum. And on top of that, I'm going to get stuff with KQ, which will be the PI equals 1, PI equals 2 components. And together, all of these guys, when I sum them up, are going to give the PP bolded structure. So this is the first thing that's going to the second thing that's going to happen is that all the couplings are going to be corrected. So that means that if I started from some massless coupling C, then it's going to now have some correction that goes like V over lambda plus higher order things, and all these guys together are going to give the low energy C, or let me call it CIR. And the last thing that's going to happen is that the propagators are going to become massive because of these extra Higgs lines. Now, I'm not going to talk about this because, first of all, it's kind of trivial. I mean, this is what you expect to happen. And it's, there isn't anything too interesting there. And the second reason is that I'm not so interested in this because I'm mainly going to be interested in what happens to the EFT couplings. And then I just care about the contact terms themselves. Okay. So let's see how each one of these things happens at the level of on-shell amplitudes. And again, I'm going to do an example which is going to illustrate how everything works. So let me talk about one. So let's suppose that I have some high energy amplitude. There's a bunch of legs, and here is a vector leg. So this is now the high energy theory. Everything is massless. And if this guy has momentum k, then the amplitude comes with a factor kk. I'm assuming for just for concreteness that this vector is positive helicity, but we could do the same if it's negative helicity. But now there's going to be another amplitude in my high energy theory, which is exactly the same, only this only instead of having a single vector, I have two Higgses here. And let me take this one to be, let's say this is K and this is Q. Now, I'm not talking about Feynman diagrams. I'm talking about amplitudes. I'm just saying that there is an amplitude with a single vector leg, but there's also another amplitude where instead of a single vector leg, I have an H and an H dagger. So now you see what's going to happen. If I now take Q to 0, the momentum of the extra Higgs to 0, then this propagator is going to become on shell. So let me, so here the momentum is K plus Q. Let me call this guy eta. And it's going to be on shell. So it's going to give me a factor 1 over K plus Q squared. But we know exactly what the amplitude does when something like this happens. It factorizes on the product of this amplitude over here times the 3-point amplitude over here. Yeah. Excuse me? Everything is massless. Yeah. Yeah. Everything is massless. Yeah. So this thing is right. K plus Q squared is going to 0 now because Q is going to 0. Okay. Yeah. No. You're right. Everything is massless. Okay. So this 3-point amplitude, I know what it is. It's something that you can work out from what you said yesterday. It's equal to eta K eta Q divided by KQ. And you say that it has the correct little group behavior because eta is a vector, so it appears twice. And K and Q appear upstairs and downstairs, so they don't contribute. And indeed, these guys are scalars. So that's what we have there. And when you take all of these guys together, when you multiply this piece by this piece, you'll see that what this whole thing is going to give you is it's going to give you a K Q factor. So this is precisely what we want. So this is going to be the P1, P1, and this is going to be the P1, P2. And you see that this amplitude with an extra Higgs leg basically gave us the subleading component in this spinor structure. So when we do all of that together, we'll get the full spinor structure. And there's another thing that's very nice that you can see from here. So remember that we need to symmetrize over the little group indices, which corresponds to symmetrizing over K and Q, because these were our P1 and P2. So what you see here is that it's exactly the same whether we exchange K and Q here, because I can put H digger up here and H here, and it's going to be the same. So we get this one, too. Oops.
Sorry, one question.
Yes, let me just,
Sure.
something funny happened to my, good. Yes.
If I take Q to 0, then I basically, my 3-point amplitude basically becomes a 2-point amplitude.
See, I don't know, that I never do, okay?
Okay.
So, I mean, here I don't want to, in the 3-point amplitude is the smallest thing that I can start from, because if I talk about on-shell stuff, there's no such thing as a 2-point. I never talk about propagators.
Then let me ask this way. The external particle, is this a Higgs or is this a gauge boson?
This one here,
Yes,
these are Higgses.
these are Higgses. So what I get by this is the coupling of 3 particles to a Higgs.
So actually the thing, so what's, okay, so that's a very good question. The thing that's happening here is like this. This is the Higgs that I'm taking, this Q I'm taking to 0, right? So this is as if I'm setting this guy to its VEV. So the thing that you can think of is just like setting this guy to the VEV, and then this guy is precisely the longitudinal component of the vector boson. So you're getting the mixing.
Okay.
Yeah. So if I had different colors, I don't think that I have. Let's see. Yeah, I do have different colors. Great. So if you look at what's happening here, is it's this story. There's this gauge boson here. There's this guy that I'm setting to its VEV. So this is like putting this here. And then there's this guy. And this is the goldstone. And you see exactly the mixing of the vector and the goldstone. Yeah.
So in that case, we're considering a coupling between the 2 Higgses and 1 gauge boson we started with, and then now we're saying that that can represent a gauge boson which has already eaten up a 1 Higgs, so that we have a massive gauge boson there. But then, like, in order to capture the exact massive gauge boson from that setting, then shouldn't we also include all the other configurations, like 1 gauge boson to 3 Higgses and 4 Higgses?
Yes, exactly. You're right. So I should, so this, I just showed you, I just did the leading order thing. Okay. So in other words, I sort of work to order V or the mass. I'm assuming that all my masses are the same order, like V. And this is the leading order thing.
Okay, thank you.
Okay, good. Okay, so that's the So that's the first thing that we said is going to happen, namely that the massless spinor structures are becoming massive. So you see that it gives you a very simple way of thinking about the Higgs mechanism, or a very simple prescription to doing this on-shell Higgsing, which is that the massless structures are just becoming bolded. And we see how it happens explicitly. So it's just being bolded. And if you think about what this bolding really is, so you see, if you think about it this way, the only thing I need to know is about Lorentz. Here I have something that transforms under, in a certain way under Lorentz, and all I'm doing is to say Lorentz tells me that it's got to be bolded. So essentially what's happening is that this one is transforming under the U1 little group. But now if I want to make it massive, I need to make it covariant under the massive little group, which is SU2. So what's really happening here is that we're covariantizing with respect to the massive little group, which is SU2. So just like in the case of the gauge symmetry itself, the gauge symmetry we saw, we can really attribute to Lorentz and the properties of the S matrix. And in this case too, we see that the Higgs mechanism is really simply arising from Lorentz. There's just no other way to do things. The Lorentz symmetry tells us exactly how things should behave. Okay, so I wasn't going to do this at this point, but let me do it here anyway. So we have this very simple prescription for how to do the Higgsing. So let's say we start from massless amplitude in the UV, and we go to massive amplitudes in the IR. So the first thing that we need to do is we need to bold all the spinors. So that means that if you have a fermion, then the fermion simply becomes bolded. If you have a vector, this also just becomes bolded. And then the more interesting case is a scalar. So suppose I have a scalar in my high energy amplitude. It's a massless scalar. So first of all, it just gives rise to a massive scalar in the low energy theory. So my momentum P here is just becoming a massive momentum. But there's something a little more interesting, which happens if the scalar momentum appears in some spinor structure. So for example, I can have something of the form 1p3, where this p is a scalar momentum. So let's say the scalar is I. So in some cases, I can have something like a bunch of indices, and then some I, and then something else. And in this case, there are two things. First of all, this is going to give rise to a scalar amplitude, yeah, let me write it. This is just going to contribute to some scalar amplitude, and it's going to be exactly in the same form. So the only thing that I need to do is bold this momentum. The momentum is becoming massive. But the other thing that's happening is that the same thing also contributes to a vector amplitude. And how does it contribute to the vector amplitude? So again, it just follows from bolding. So I can write this guy on the left. I can write it, for example, like this. What it is exactly depends, of course, on, you know, how many indices I have on the left and how many indices I have on the right. But I can always write the momentum as II. And then when I bold that, it now becomes I and I, like this, and whatever else I had. So now my I is appearing twice and carrying the correct little group weight for a massive vector. So this is now a massive vector amplitude. And you also see that the highest component of that, because I have an angle square, is precisely a longitudinal vector. Okay? So what we're saying exactly is the Goldstone theorem. Namely, I had a scalar amplitude that generated a vector amplitude at low energies, but it wasn't just any scalar amplitude. It was a scalar amplitude where the momentum appeared. It had to appear explicitly. And what does it mean? It means that we have something that's derivatively coupled. Okay? The fact that I have the momentum in momentum space means that I have the derivative there. And this is precisely the thing that you expect of a Goldstone, which becomes the longitudinal component of the gauge field. Another way to think about the same thing is that what we're saying here is the Adler zero. That is, for any Goldstone boson, we know that its amplitude should vanish when we take its momentum to zero. That's the Adler zero, and that's exactly what we see here. So you see that the main elements of the Higgs mechanism, you just get them for free, and they all just follow from Lorentz. Okay, so I think this is really remarkable. It's really beautiful the way it happens. Yeah.
Meaning of QUC and vector interface, because if we have one indices, we can imagine one fermion, and if we have two I indices, we can imagine a vector particle. So in the upper case, there is one I indices.
No. Okay, so let me just start. So maybe I wasn't clear enough. What I meant was that suppose you imagine an amplitude. So I have an amplitude with a bunch of legs. Okay. And let's just look at one particular leg, I.
Yeah.
If this I is a fermion, then the amplitude has one power of this massless spinor I. It can be square, it can be angle. Okay?
Yes, yes.
And then when and then what I'm telling you is that what I need to do is to just take that and bold it. And that's going to give me an amplitude in the low energy theory that has a massive fermion instead of a massless fermion.
Yeah.
So I'm just talking about a single leg I of the amplitude.
Okay.
Okay, and in principle, you have to do this for all of them. And the place where I'm going to use this is when I construct the contact terms of EFT, of effective field theories.
I see. Thank you so much. Yeah.
Okay. Any more questions before we go on? Okay, good. The second thing that we said is going to happen is that couplings in the low energy theory are going to arise from couplings in the high energy theory. So let me also talk about that. And again, my main focus is going to be the Wilson coefficients of EFTs, but it's convenient to mention this here. So again, let's start with thinking about the UV theory with where all the masses are 0. So here I can have all sorts of amplitudes. Here is something like this, 1, 2, 3, N with some coupling C1, and then, and actually let me make this more precise. So here I'm really talking about couplings. Okay, these are contact term couplings or contact terms in amplitudes. And then there's another one that I can write down that has one Higgs leg and comes with some C2. And then there's going to be another one that has 2 Higgs legs and comes with some C3, and so on and so forth. Now, depending on your theory, in the standard model, for example, if C1 is non-zero, then C2, where I just add 1 Higgs leg, that guy is not going to be non-zero. But C3, where I have an H and H dagger, that will be non-zero typically. But in general, this is the sort of thing that you can have. And when I set these different Higgs momenta to 0, when I take their, so this is Q, for example, and this is Q1, Q2. And now I want to take all these Qs to 0. The thing that you'll get is that you have C1 plus V C2 plus V squared C3, and so on and so forth. And this is all going to sum into your low energy coupling. Okay, so this part is very simple. Okay, so at this point, we have a pretty good understanding of how the Higgs mechanism works in this case. And now I finally want to get to some applications and specifically talk about EFT applications. But by now, we really have all the tools that we need. So let me talk about the construction of EFTs in this language. Okay. So let me first of all say a few words about EFTs. Yeah.
So if you have fixed insertions, then in some cases we can have chirality flip.
Exactly. So the chirality flips are exactly the things that I discussed before, precisely. And in this case, you see that the things that are, what's happening here is more like a shift of the coupling. Okay, but in the standard model, so the thing that we saw before was precisely the chirality flip. If I repeated this for a fermion, then it would be a chirality flip. And here you see that in the case of the standard model, if, for example, this guy is non-zero, then C2 is going to be 0, because I cannot just add another one doublet, and so on and so forth. And so I'm going to get C1 plus some V squared over lambda squared C3, blah, blah, blah. So I'm always going to get corrections that go like V squared. But on the other hand, if my C1 was 0, meaning this is something that does not appear, that's forbidden in the standard model, then the first thing is going to be down by V.
Then if you have a chirality flip, then wouldn't the coefficient be proportional to the mass of the
So
fermion?
yeah, exactly. So if so I wouldn't call this a chirality flip. The chirality flip is more the thing that we discussed before. So we looked at something like this, and I can also look at something like a fermion and a Higgs and another fermion, this is the chirality flip. But if you're talking about the shifts of the coupling, if there's some coupling that's forbidden, let's say the dipole coupling is forbidden, it will first arise with a V. That's the, okay? Okay. Good. So there's been a lot of interest in recent years in effective theories. And to some extent, all we ever do in physics is effective theories. Because when you're studying some physical phenomena, you usually have to care about a certain subset of the Lagrangian. Like if you do atomic physics, you don't need to know the full standard model Lagrangian, right? So the question is always, what's the experiment that we want to describe? What's the relevant energy? What's the detector resolution? This is what's guiding the theory, okay? But the reason we're very interested in this question, in EFT constructions, is that we know there are some things that we don't know. In particular, we talked about electroweak symmetry breaking and what's the origin of that. We want to describe that in a way, or we want to try to measure that or probe that in a way that's model independent. And this is what EFTs let you do. So here you can take a bottom-up approach and say the following thing. We say, what's our input? The input is the fields that we have at low energies. The input is also the symmetries. And these symmetries include the global symmetries, the gauge symmetries, and of course, Lorentz. And out of that, you construct the most general EFT Lagrangian. And from the EFT Lagrangian, you calculate the amplitude, and then you go to experiment, and you parameterize the experimental results in this way. So what people mostly talk about is the thing that's called the SMIFT. And what is the SMIFT? So in the SMIFT, the first thing that you want to do is to write the SMIFT Lagrangian. So this involves all the standard model fields, Q, U, D, L, E, the gluon fields, the W's, the B, and the H doublet, the Higgs doublet. And the symmetries, the symmetry that we impose is the global symmetries and also the full standard model gauge symmetry. And the first thing that you need to do is write this Lagrangian. So this is what, when I say the SMIFT, this is what I mean. The Lagrangian in terms of these fields that respects this symmetry. And there's something you can write down at dimension 6 and something at dimension 8 and so on and so forth. Okay, now writing this Lagrangian, as you may have heard, is very complicated because there are many operators that go in, and many of these operators are not independent. If I try to write down a set of operators, they are usually related to each other, and it's not that easy to write down a set of a basis of independent operators. And in particular, the things that you need to deal with are integration by parts. So I can write some operator using integration by parts in terms of other operators. I can convert between operators using the equations of motion. There are field redefinitions that I can do. So it's all pretty complicated. But suppose I did all that and I found some basis of operators, so I have this Lagrangian, then this isn't the end of the story, because now there's more work to be done. Because at the end of the day, I want to compare to experiments, so I need to work with physical things. So now the thing that I need to do is I need to turn on the Higgs wave. And when I turn on the Higgs wave, lots of things happen. For one thing, all the couplings shift. Because I have all these higher dimension operators in my theory, and some of them involve the Higgs. And now I set the Higgs to its VEV. So everything is going to get corrected. And in particular, even the gauge coupling is going to get corrected by things like this. And at higher orders, more things, and so on and so forth. And also all my wave function renormalizations are going to be corrected. So instead of being 1 at tree level, there is also corrections like this. And all the masses that I had at tree level, let's say some m squared, also gets corrections like this. So everything gets shifted. And so what I need to do at this point is I need to redefine fields to go to some canonically normalized fields. And I need to redefine my couplings using some inputs in order to define my couplings, using some experimental inputs. And the last thing that I need to do, which is also not that easy, is to derive the Feynman rules in this theory. And this is a massive gauge theory. So I can work with some RXC gauge, for example. But whatever I do, it's complicated. Okay, so it's not simple. And this is one thing, or there are many things in the story that the amplitudes can bypass. So what can they bypass? So of course, with amplitudes, there are no issues of field redefinitions or integration by parts. You're just using the on-shell quantities themselves. So the task of writing a basis of operators becomes much, much simpler. And we'll see an example. And the other thing is that, as we saw before, you can work directly in terms of the physical quantities, and then you can bypass all of the second stage too. Okay, so now let's think about how to do this on shell. So we want to do exactly the analog of this, and the analog is very clear. And it's actually something that we already did. What we did was to write down the most general amplitude. And when we write down the most general amplitude, we get both the renormalizable part and the non-renormalizable part. It's like, no, there's no choice. So here we start from the physical particles. And the other input is the global symmetries. I could also put in the gauge symmetries as input. But if we don't do that, as we saw, it's going to be forced upon us by consistency. And then we will write down the most general amplitude. And there's going to be a one-to-one correspondence between the two. Which is not surprising. Because, of course, if we write some EFT Lagrangian, it's got some number of operators with some Wilson coefficient Ci. And that means that when we calculate an amplitude, let's say this is some On with n fields, so it's going to contribute to some amplitude, and this Wilson coefficient Ci is going to appear in the amplitude. So there's a one-to-one correspondence between these operators and the contact terms. Okay, and the other thing that I want to emphasize is that, you know, you can use the on-shell stuff in order to learn all sorts of things about these operators and Wilson coefficients and count them and classify them and things like that. But at the end of the day, the thing that you really want is the amplitude anyway. So if you get the amplitude directly anyway, you can ask, why bother? You know, why do I need to use the amplitude to learn about the Lagrangian and then do this complicated business of that we described up there to go to the low energy theory and calculate the amplitude again? So I just want to concentrate, or I can concentrate if I want to, on the physical thing that's the thing of interest. Okay, so I have just a little more. So let me see, I can think of two possibilities. One is to go on for a little more now, maybe it's going to be another 10 minutes or so, or the other is to do this during the discussion. What do people think? Discussion. Okay, does that seem reasonable? Okay, very good. So we'll steal something like 15 minutes from the discussion and continue then. Okay. Okay, more questions?